Is SST separate from the Tuck campus?
In terms of electricity,
Electricity and heat?
it is in heat because there are two separate meters
Okay.
for the gas. In terms of electricity, there is only one meter, but we can still measure individual panels. And so if we get down to a really small area, we can actually measure a circuit and we can actually log that data and measure it. But I have a feeling, just by walking through myself, there are some pretty reasonable projects that could have a significant impact. Over on this side, have you ever been in the hallways when the lights are off here? They turn on their own because of the sensors. They don't have that in the other building. And the other building has the big fat light bulbs. This building has the real thin, smaller ones. Those are the much more efficient ones. Each of these lights out in the hallway only have 2 lights. Over there are 4. And so you have not only worse lights, but more light bulbs and no occupancy sensors. And I realize that a light really doesn't use a heck of a lot of electricity, but you have to think that those lights are on 9 or 10 hours a day, and there's hundreds of them. And so by the time you get done, you can see a pretty significant change. The Strata Middle School recently went through and relamped their entire building, and they're saving somewhere around $70,000 a year. So,
is there a spike on the ballast when electricity is turned on to power the lights? Does it draw more of a spike and then taper off as they're on?
I don't think so. I've never heard of that. I think that it just sends a constant current because it's phosphorus or whatever's inside that fluorescent tube, and it doesn't require a spike to push it through that resistance level.
Okay.
But the spike question is an interesting question on the utility side. We always think of energy costs being related to how much you use, and that's your generation, and then you don't get this in houses, and so that's why you don't really see it too often. But you get charged when you get an electric bill in a big building for what your demand is. And that is, some of the engineering students and I saw the waveform for how a day of electricity or a week goes. When the utility company takes your peak day, and they bill you based on that. So the higher that peak goes, the more you get billed, and it doesn't matter how much electricity you use overall, they bill you for the peak. And the reason for that is they have to invest a huge amount of money to make sure that the pipes getting to your building are fat enough to accommodate the electricity. And so you have to understand that you have to trace that pipe all the way back to the power plant. And so each person who goes onto the grid, they get a constant amount of electricity, but then the utility company has to add up all their demand and make sure that the pipe and the equipment and everything is big enough to accommodate the peak loads. And that costs a boatload of money. And if it's only 1 day a year or 1 hour a day that you reach that peak, they have to somehow recuperate, they have to get their money back. And so what they do is they bill you based on your demand. I've seen electric bills where the demand is the same price as the generation. And so if you could shave off the demand, you could save 50% of the electric bill. And if you're talking about a building like this that's paying $500,000 or $200,000 a year, now you're talking about a real significant amount of money. And the funniest part about this, you can do this kind of stuff by behavior. So what we looked at a power curve for the high school, 1 day, and it goes along, and then at about 6 o'clock it goes from 180 to about 1,200 kilowatts in a course of 15 minutes. And what happens in that time? Everybody gets there and turns on the lights and turns on the computers and opens the refrigerators and turns on the coffee makers, and everything fires on at the same time. And sure enough, that's the time that the utility bills you. If everybody came in at different times and tried not to turn everything on at the same time, you could get to the same level, but you wouldn't get this huge peak, and then you wouldn't get socked with that giant demand charge. You hear about things called, it's a VFD drive, a variable frequency drive. A lot of large motors, they'll start up at 1 speed, and then they'll go to a 2nd speed, and then they'll wait 15 minutes to get up to their full run speed. And the idea is that when they turn on at their full speed, that requires a huge amount of power. If you have an air conditioning or another kind of fan in your house, sometimes the lights dim when those units come on, and that's because of the demand being sucked in by that motor. And so a variable frequency drive is a mechanism for people to control demand charges. It has nothing to do with the amount of electricity that it uses, It's how much that electricity pulls instantly. So, one thing, so we talked about some potential projects. One of the ideas was looking at another solar array that would be installed here, or looking at the possibility of doing a wind turbine, or trying to do a solar thermal array, if we can find a place to do where there might be hot water. Now, we've never really talked about solar thermal because we're not doing that. The hard part about bigger buildings is, in like this building, it has a continuous loop of hot water, meaning it is constantly running hot water through this building, because the hot water heater is way the heck over there in the boiler room. So when you turn on the hot water in the bathroom on this side of the building, it's hot. It's not because it just sends it, it's because it's constantly circulating through. And that is not the most energy efficient way to do it, but it's the next best way to do it. If we can isolate a load somewhere, we might be able to put up a solar thermal array, and this is how it works. Have you ever seen the tubes, the solar tubes?
Talking domestic hot water now
Yeah,
for this?
yeah.
It's okay, domestic.
Or if you have a floor with a radiant, you can use solar thermal to heat a radiant floor. But I don't think you have something like that here. You do. I saw plans that say you had a snow melting system. Is that actually, did that get installed?
Not sure.
Well, either one of those cases could use solar thermal. What you have is an evacuated tube, and in it is a flat black metal sheet. And in the center of that sheet is a tube with glycol in it. And so when the sun, even though it's 30 or negative 30 outside, the sun shines, because it's a vacuum, there's no temperature in here, and that black metal heats up. In fact, some of these systems have to have heat dumps on them because the glycol gets up to 190, 200, even 230 degrees. And so you can end up with like a blowout on one of the clamps. What happens is it runs water over those glycol. The tubes fit up into a header, and then the water circulates around the tubes until it gets to a set temperature, and then a pump kicks on, and it kicks the warm water into your thermal tank, and then that becomes the source of your domestic hot water. Now, in solar thermal, if you have an extended period of cold or cloudy, you always have to have some kind of backup system as well, particularly if it's a house. So you may have a low-cost, high-efficiency Insta-Hot system, or even a small propane system, or something like that. But the idea is that you take as much heat as you can from the sun, and then you don't have to be paying for propane, natural gas, or oil, or whatever way you do it. But these systems are relatively affordable. You can buy a system for a house for about $7,000, and it would possibly, it would take about 90% of your thermal domestic supply, and it lasts for about 10 or 20 years. 20 years, 10 for the pumps and things like that.